activities in Japan.
Thank you, Jeff. Good afternoon, everyone. I'd like to introduce about recent SPS concept and activity in Japan. I'm Koji Tanaka from ISAS JAXA. This slide shows a brief history of solar power satellite. Study of solar power satellite have a long history. This year is 50 memorial years, and also Japan has a little long history, SPS study long history. First research meeting in Japan was held in 1979 by CRL. CRL is a communication research laboratory in Japan. Also after that, Japan academic study group or some academic activity started, and especially around 2000, USEF present J-Space Systems and JAXA, NASDA present JAXA started a research study on solar power satellite. Among these study activities, some conceptual study on solar power satellite were performed. And also in Japan, many WPT demonstrations were carried out during many years. This shows the four major conceptual studies in Japan. One is the 1 gigawatt ground design by NEDO, and around the beginning of the 90s, SPS 2000 was studied by ISAS group, and also USEF and NASDA studied their conceptual solar power satellite studies. These two figures shows the conceptual study on solar power satellite performed in early 90s. Right figure shows the ground design by NEDO. This study performed based on the NASA and DOE's reference system studies. This study targeted on the commercial-based solar power satellite. This is a very big satellite. Total mass is around 21,000 tons. This satellite selected a transmit frequency with 2.45 gigahertz. And also, left side figure shows the SPS 2000. This study focused on the realistic solar power satellite available only near future technologies. So this is a very small satellite, and this satellite's total mass is only 240 tons. However, transmitted power is only 10 megawatt, but requirement number of launch is only 60 times using Ariane 5 rocket, and orbit was selected. Equatorial orbit altitude is around 1,100 kilometers. And these two figures shows the recent 1 gigawatt class commercial-based solar power satellite concept studied in Japan. Right-hand side figure shows the JAXA models. This model have a very complicated figures, but this satellite can provide electricity stably because this satellite adapted very large concentrator systems. But this system requires a far future technology. So left-hand system, this is called tethered solar power satellite, studied mainly by J-Space Systems. This model targeted or focused on the feasibility of the solar power satellite. So this system adapted non-sun tracking power generation systems, and altitude is controlled by the gravity gradient stability systems. So this output of this solar power satellite is varying by time. After that, I will explain the detail of this tethered solar power satellite. Before studying of this solar power satellite, we re-examine the requirement and problem of the solar power satellite. This is the main problems to be solved towards the solar power satellite. One is the large-scale power generation in space environment. And next is the wireless power transmission technology. This is an inherent technology for solar power satellite. And also construction and control of a very large-scale structure. This is one of the biggest problems. And this lifetime of solar power satellite depends on the space environment resistance of the components, device, or something. And low cost and mass space transportation. This is one of also a big problem for solar power satellite. We evaluate each problem and listed the significant problems of solar power satellite in past concept studies. Rotating power transmission mechanism. This requirement results the lack of the robust design and single point failures. Also, requirement bus power collection. This requirement from such as a NASA reference system or Sun Tower, NASA ISC. The system requires bus power collection. This requirement results in practical weight of cables. Also, in case of superconducting cables, this is a very distant or far future technology. Also, such as a NASA SSPS model or NASA ISC, these models requires a concentration mirrors. This results heat waste or it has a difficulties of sun tracking system for large thin film structures. Also, some models will be considered will be operated after all functions are constructed. This requirement results a risk of development and investment, and this requirement is unacceptable for commercial-based solar power satellite. Also, many concept study or many concepts of solar power satellite demonstration and commercial solar power satellite have been considered separately. So in this case, lack of the consistent, it is difficult to make the consistent roadmap between demonstration and commercial solar power satellite. We evaluate such significant problems and we perform the trade-off studies. And this is one of example of the trade-off. This is one of trade-off study concerning on the sun tracking systems. Left side shows the concept with the sun tracking system. Sun tracking system consists of very large-scale mirror and large-scale rotating mechanism. This technology is very difficult. So we adapt non-sun tracking systems, only plate. Such trade-off study, after such trade-off study, we studied a multi-tether solar power satellite. This satellite consists of the same sub-satellite depicted in this left-hand side. This sub-satellite, the size of this sub-satellite consists of this size of the sub-satellite is around 5 meter times 95 meter, and compiling this sub-satellite final multi-tethered satellite was built up, and this satellite can provide 1 gigawatt output power. This is a spec of multi-tether solar power satellite. Size of main plate is 2.5 kilometer times 2.375 kilometer, and with a thickness of 2 centimeters. And this satellite consists of 625 sub-satellites, and sub-satellite consists of same structural panel. This is the main feature of this tethered solar power satellite. And frequency is selected 5.8 GHz, and output power from rectenna designed to be 1 GW. This is requirement technologies for tethered solar power satellite. About the power generation, efficiency is required 35%, and specific power is 2 kilowatt per kilogram. About the wireless power transmission technologies, efficiency required 75%, and 10 gram per watt is required, and very precise beam control also required. And about the rectenna, efficiency is 85% is required. And for transportation cost, 15,000 JPY per kilogram. This is supposed. This table shows the cost estimation of tethered solar power satellite. Total cost to build solar power satellite estimated to be around 11 billion US dollar. And space segment estimated to be around $5 billion, and ground segment estimated to be $2 billion, and transportation cost, this includes RTV plus OTV, this is estimated to be $4.3 billion. In this estimation, launch cost is assumed to 90,000 US dollar per ton. Also, annual maintenance cost is estimated $300 million per year. And in these cases, unit cost of electricity generation becomes 8.3 cents per kilowatt hours. This is a summary of tether specification and requirement of tethered solar power satellite. This part is a requirement for launch systems. And in this study, we consider the case of output variation type tethered type solar power satellite. This figure shows the daily power demand or daily power supply. This figure shows tethered solar power satellites is initial introduction models. The power generation amount of the tether SPS varies with time. However, red solid line shows the output from 50 tethered SPS. Maximum provided power is around 50 gigawatt. These practical variation can be adjusted within the hybrid of various ground-based power generation systems. So we think for the early realization of solar power satellite, we also consider that the output varying type solar power satellite was meaningful for initial installation introduction cases. In order to realize the tethered SPS, this is a mission scenario towards the practical model. First phase is a ground demonstration on wireless power transmission, and the next phase is small satellite space experiment phase. This includes the structural experiment and wireless power transmission experiment. After that, large satellite phase were planned, and last is the verification plant phases. Verification plant can evaluate and verify the system of the solar power satellite. And in Japan, already many WPT demonstrations were performed, and especially around 2050s, very precise wireless power transmission demonstration experiment was performed by JAXA and J-Space Systems. in initial roadmap, we would like to move space experiment phase after this experiment. However, in this situation, we would like to move space experiments around these phases, but this roadmap was changed. So movement of the space experiment was postponed, and this is one of revised roadmap. This is by JSpace Systems, and JAXA makes other roadmap towards the solar power satellite. So now we are adjusting roadmaps. In this roadmap, decision of the moving space experiment may be decided around 2025. After that, space experiment started. And this is summary and conclusions. In the 90s and the beginning of 2000, major Japan's SPS conceptual studies were performed, and 4 major concept study design. And JAXA and JSpace Systems carry out the ground WPT demonstration towards the tethered SPBS. But next space experiment was cancelled because of the roadmap was revised, and so now we are developing a critical technology, especially structure and wireless power transmission technologies for the solar power satellite. Thank you for your attention.
All right, our next speaker is John Mankins, who is not only the chair of ISDC this year, but also the organizer for this SPS symposium, as he was with Gary. And he, for those of you who were at the Kobe SPS symposium, he's no stranger, and probably for other reasons as well, and also in 2009 in Canada. So he's been a figure in SPS for quite some time, and has actually written a book, you may be familiar with it, The Case for Space Solar Power. So please welcome John.
Oh, okay. Where'd the computer go? Where's the computer?
It's right here. There we go.
Whimper, whimper.
Oh, you wanted a computer.
I can do hand puppets.
Let's see it.
It's tough. It's tough. Let me show you what I can do, Gary. Excellent. Okay. Probably the USB port.
Windows machine will show you.
Yeah, front and back. So let me once again put in a plug for everyone who's making presentations at this symposium to please get your slide decks in, not necessarily videos unless you want to share videos, but get your slide decks in. I'm not going to say that again right now. I'll say it again later. Thank you very much, Paul. I was careful to highlight Gary Barnhart's role in co-organizing this event because he did much too much of the work for me to ever neglect it, and I appreciate it. So thank you. If you neglect your partners, they don't help you next time.
I'm in trouble.
No. Only if all of my gin is gone. Okay. So clearly, I need to add more videos. So I'm going to apologize for no videos. I've tried to stick strictly to the SPS alpha concept. I will mention that that there are copies of my book on sale. No, it's not true. It's not true. Strictly, as it happens, the book is available on Amazon. I don't get a penny. If you buy from Amazon, 70 cents on the dollar goes to Amazon, and the other 30 cents on the dollar goes to my publisher. So next time I'm doing it differently. So I thought it would be fun to start with the first solar power satellite. So this is my version, my rendition of the conceptual illustration, just basically a proof of concept from Peter Glazer's 1968 paper, since a major theme of this SPS 2018 is 50 years of solar power satellites. So in this case, building on ECHO, which was fresh, I think, in Peter's mind at the time, that was the deployable, inflatable, spherical reflecting satellite that didn't do anything, you just bounced radio signals off of it. This was a spherical solar array as a concept, details to be determined. Then a superconducting power management and distribution cable, and down at the base, a microwave wireless power transmission system going toward Earth. The whole thing was to be approximately gravity gradient stabilized. Sunlight would come in basically from any angle, and the power would be transmitted to the Earth. Peter, as he said in the remarks that I showed earlier, did not intend to have the design, only to show the concept. And so, but I like very much the similarity between Peter's original concept and SPS alpha. I get rid of the sphere, and I get rid of the superconducting power management and distribution, and I get rid of the huge kilometer scale power management and distribution across the platform. But as I will be describing in just a few moments, I'm going to hope that the laser pointer is up here someplace. Is it down there?
Red or green?
Red. I like the green better, but the red has more intensity. So, in case you're unfamiliar with SPS alpha, the central drivers for this architectural approach had to do with getting rid of the very large single points of failure that existed in some of the NASA concepts from the late 1990s, in which reflectors were used to redirect the sunlight, also to get rid of the power management and distribution system in large measure, by going towards the concept that was pioneered first in the 1980 time frame by, I think it was Owen Maynard, who has the patent on this, but I'm not positive. I think it's Owen Maynard. And then later in the solid state implementation by our Japanese colleagues, including Professor Nobuyuki Kaya, in which the sunlight comes in. In this case, the large reflector arrays are disposed of. There are an array of very small reflectors, not tiny reflectors. These are all on the order of 40 meters in diameter, depending. These are independently steerable. Sunlight is directed, redirected. On this side of this transmitter, PV converter is PV, obviously. Then there is structure in between, and on the other side is the RF transmitter, which sends the power down to Earth. This is a somewhat greater detail. The stepped cones are a variation on the original SPS alpha configuration, which if you've seen it, looks a bit like a margarita glass. The dilemma that I had with that is that it's very much it's an infinitely variable problem, so it's very hard to mass produce other than a single ring of these reflectors. In this architecture, if you were standing here looking up at the Earth, and the center of gravity is approximately here in this platform, and it does rotate obviously once every 24 hours, you would have something like 10 to the minus 6th or 10 to the minus 8th Gs. So you could actually stand here and you look up, what you would see would be like a Roman amphitheater. It would be like standing in the Colosseum with row upon row of steps. And on each step there is sitting not an individual but a mirror. And the mirrors are all attached by simple articulated and mass-produced robotic arms, which I'll show in a moment. Truss structure between the two, connect and multiply redundant truss structure. I should mention very much like a Hoyt tether, if you've seen that concept. And at the base is the transmitter, PV on one side, RF on the other side. Another thing just to highlight, which I'll mention again in a moment, is that the reflector array is oversized, and there are additional small trim sails here at the base. The total area in the cost and mass estimates, which I'll show you in a moment, are sized so that the north-south station keeping, about 50 meters per second in delta V, for the SPS Alpha platform is provided not propulsively, but using solar pressure. Still some necessity for onboard propulsion, but to a large extent, the propulsive requirements are passive. This is just another highlight, shows things somewhat blown up a little bit. I'll zoom in on this in just a moment. So the backbone structure, PV arrays, the secondary thin films here for purposes of attitude control, the RF transmitter array on the base, looking down from above, looking up from below, and you can see the rows of seats, as it were, in the perspective view. This is now zoomed in. You can see the individual reflectors. All of the reflectors are exactly identical in size and shape, and therefore are amenable to very large scale mass production. Each one is attached to this frame, which is a standard frame. All the gaps between the rows are the same by these articulated arms. I will mention you cannot see it here, but there is a particular platform here at the very center, which I describe in my writing as the kernel. I followed the construction technique pioneered by the space station, where originally this core platform was going to come from the Naval Research Laboratory. I forget the name of the module. Somebody know. The interim control module, and then it ended up being the Russians who provided it. But nevertheless, the idea of having a single platform for this kind of architectural approach that uses highly structured but largely repetitive but very large scale construction, having an initial place to be deployed to the operational orbit, and then have all of the subsequent flights go to that location. In this case, it's here, it's this kernel, and then you build down and you build out row by row, and then you continue on down to the base. I thought it would be nice to add an example from last year's Space Solar Power student competition, in which one of the teams, actually at the Harbin Institute of Technology, dug in on SPS Alpha and did a modeling simulation of how these mirrors might work, and basically using an adaptive control scheme. What they found is that if you define a function for the mirrors to satisfy, that you could use them to essentially create any shape you wanted on the backplane of the PV array. So these are actual simulations that they ran, and they basically had a control loop. So in this case, it's just circular with a slight Gaussian. In this case, they did it as a square for fun. They found that they could make the mirrors, because there was a large number of them, and because each one produces a Gaussian image of the sun on the PV array, that you could create very high uniformity with the power distribution across the PV array that you might wish, which was really nice work. I'm looking forward, tomorrow afternoon we've got the results of this year's SSP student competition. Is Peter here? Peter? No, I don't see him. Peter Schubert? Is he here today? No. I want to apologize to him. I meant to specifically apologize yesterday because I didn't inform him. I didn't remind him that we were having the competition this year. If all goes well, and I think tomorrow's competition is going to be really good, we are going to do it again next year, so please be on the lookout for this. It's a very nice opportunity for students to get involved in the project. Essentially, the purpose of the modular concepts that Tanaka-sensei talked about a moment ago in the 1990s was to get rid of the big power management and distribution backbone from the concepts, and the big rotary gimbal from the concepts of the 1970s rather. Purpose of SPS Alpha is to then go a step further and get rid of the single points of failure that existed in the reference system concepts, the reference concepts from the late 1990s. Does rely on an assumption of fairly high efficiency solar power generation. I will mention that using the results that came out of the NRL studies, there is a limit in the analysis of not more than 3 suns concentration ratio from this array of reflectors down onto that transmitter array, the PV array on the backside of the transmitter array, and everything else is sized accordingly. So if there is a variation in this percentage, then it automatically drives. If you drop to 30% or 25%, then it automatically resizes everything so that your concentration ratio drops to keep the temperatures at a temperature load of about 80 degrees C. So that's the assumed temperature in these numbers. Wireless power transmission is assumed at about 70, with the expectation that there's work going on both in the US and in Japan, raising those numbers to more like 80% efficient power amplifiers. It's all in-space assembled. There are no large kinematically deployed mechanical structures. The low mass thin film deployable erectors are on the scale of Icarus, so on the order, or the DLR deployed solar sail of some years ago. The animation is available online. The local power management and distribution is all at the scale of the PV arrays through the supporting structure at the base to the transmitter array on the order, not more than a few meters distance, typically on the order of tens of centimeters of distance, with relatively low voltage. No power levels ever above 10 kilowatts going from the PV to the transmitter, and less than 5 meters in this case. Low-cost launch to space is assumed, but because the scale of these objects, and I'll come to that. Oh, yeah, I should talk about that now. So in principle, the scale of this is on the order, as I said previously, or I was on the slide previously, bless you, on the order of 5 by or 6 by 13 kilometers. These objects that make it up are on the order of kilograms. So all of them are on the order of 1 to 10 kilograms of various shapes. And so launch, I'm perfectly happy with the launch packaging on the Falcon 9 or the Falcon Heavy. I've got lots of thin, lightweight objects that are poofy, that are fluffy to put in the bulk of the shroud, and then I've got lots of heavy objects to put down in the bottom of the shroud, however the packaging goes. Critical advance recently, which I talked about yesterday, is this highly structured robotic assembly. If you look at what's going on now in robotic warehousing and robotic mining, you go with RFID tags and appropriate visual cues such as barcodes, and there's really no reason that a small complement of robots could not handle all of the materials, the approximately 1 to 3 million modules that are involved in the SPS Alpha, individual modules. I will mention that once the assembly is done, all of these robotic arms that are used in the assembly are the ones that then subsequently turn around and become the pointing systems for the reflectors. So I fully endorse Ian's observation and not wasting anything. So the robots that may do the deployment turn around and become the robots that do the pointing subsequently. And similarly, the propulsion systems that take the modules up to GEO, which is the nominal operating orbit, are the ones that then stay and provide the minimal additional propulsion that's necessary for the station keeping. So this is the design reference mission 5, which is scaled. Obviously, these are very amenable to scaling across almost an infinitely variable degree of sizes that you might wish. At about 9,200 metric tons, so about 9 million kilograms. The power output is about 2.5 gigawatts. Power delivered on the ground is slightly less than 2.1 gigawatts. The transmitter array is about 1,700 meters in diameter. Receiver diameter is about 6,100 meters. The initial platform cost is about 11 billion. Levelized cost per kilowatt hour, and that yields, by the way, for these kinds of numbers, a cost per kilogram of about $228 per kilogram for the platform hardware. If you have a cost per launch of $600 per kilogram, you end up with a cost of levelized cost of electricity of about 2.5 cents. One of the interesting features of this concept is that it's highly amenable to a very wide range of applications in space. In particular, it scales down to tens of kilowatts and up to multiple gigawatts. As a consequence, there are a wide range of applications for in-space markets. For example, you can use these for current satellite options. It works perfectly well for any kind of geocommunication satellite. But it allows you to scale up from 10 or 20 kilowatts, which is the current limit, to multiple tens or even hundreds of kilowatts, depending on the application, for very large phased array apertures. Similarly, for the Moon and Mars, you have a very nice feature, which is at the Moon or at Mars or the main belt asteroids or wherever it is, the only significant change you have to make to the platform is to add reflectors. The rest of it can stay essentially the same and be scaled appropriately. Let's see. A wide range of additional markets on Earth, including emergency markets, including premium power for niche markets, and of course in the longer run for baseload power. I used at least a couple of your charts. I was over there madly typing away. This was updated last year to add the feature of the using the solar pressure. I already talked through most of these features. It's slightly less than 2.1 gigawatts. And I already mentioned the feature being that the system is massively redundant. You had asked the cost estimate to first power for an operational SPS. And the cost estimate for the platform is about $11.9 billion. And it ain't a wag based on the earlier iterations that I've done previously for smaller scale, that getting to there ought to be about 15 billion, with about 12 billion being for the that first large-scale platform, and then about 3 billion to get to the point of beginning that project, with smaller scale demonstrations being conducted along the way. That's probably a little high, but you make the assumption that launch costs initially are going to be a little high also. And I already talked about this. And that's it. Yeah. Be cranky. Okay.
All right. Keith, you're going to use your own computer? All right. Our next speaker is Keith Henson, who has been active in space development for many years. He actually, I believe, correct me if I'm wrong, Keith, but I believe you're a member of the original member from the L5 Society. The founder, that counts. And he has been engaged ever since. You may see him active on many of the forums associated with space development and space solar power.
If any of you want to sign up with it, there's a group on Google Groups nowadays. Got a power connector there? And never mind. It'll probably get through. There's a group now called Power Satellite Economics, because the economics is, as everybody knows, is the biggest problem of the whole thing. Yeah, like here. The easiest way for me to explain what I'm talking about is I'm actually talking about a use for a power satellite, a very specific kind of power satellite called a propulsion power satellite. And the problem with everybody knows about this is the problem is getting stuff from LEO up to GEO is at least 2.5 to 1, and I've tried to cut it down to somewhere around about 1. So if you can get stuff into low Earth orbit for $100 a kilogram, you can get it to GEO for 200. This involves using a very, very inefficient gadget called a arc jet, and such things exist. Let's see if I can get it to play. and I'm going to leave the I'm going to leave off the sound here and kick kick it along a bit here, make it run a little faster. Old power satellite designs of various sorts. This is the new design. This is a particular power satellite design which is designed to provide energy for propulsion, and it is. This is this description of various and sundry things that go along with it. And let me just jump ahead to this business, showing the use of the thing and how it beams power. This is actually the receiver end of the thing. This is a 500-meter rectenna. Here we go. And this is a 50 megawatt firing into air. This is a 50 megawatt arc jet, and it generates it's around 70% efficient, and it generates 20 to 25 kilometer per second exhaust velocity, which is really ripping right along. And it means that you can do a spiral orbit transfer out from low Earth orbit to GEO with half a power satellite and about 4,000 tons of reaction mass. That's assuming it weighs about 30,000 tons for a 5 gigawatt, which is consistent with what John came up with. He got, what was it, 9,000 tons for 2 gigawatts. So that's about 40. It's a little lighter than the ones I've been considering. Anyway. These things are power hogs. This is 50 megawatts. And so in order to actually get it up there, you need about 400 megawatts, which is to say 8 of these things or 4 somewhat larger ones. And the power demand is incredible. So how do you supply power in space? Well, you can use PV, of course, but the problem of it is PV can only intercept about a kilowatt per square meter, because that's the power of sunlight, and this needs more. So I'm trying to get something in the order of 10 or 12 kilowatts per square meter, and since I don't have to worry about birds, I can go ahead and use quite a bit more power on the thing. There's a big problem which hardly anybody recognizes, which I should go back just a bit here and stop here for a second. This is a graphical illustration taken right off the space junk problem, showing the problem of trying to transfer stuff out in a spiral orbit, because what you run into is space junk. There's a whole lot of it up there, and as a matter of fact, something the size of a power satellite gets hit about 40 times on the way up. And this is unpleasant. And you have to go above about 2,000 kilometers to get out of the junk level. Can be done, of course, but it's a real nuisance. So the idea is that if you're going to haul stuff up, you want to haul it up in the form of the tightest packages that you can get. And so this is what the idea is, and you actually need 2 of them so that you can, because they're down near the Earth, you want to be able to power the things all the time. So you have 2 of these that are powering at the far end of the target. There is the rectenna and the arc jet engines. And what it's doing is it's getting it's burning about 400 megawatts of power. So in order to get